Hey, we have here today kind of an unusual integral. This one's from MIT Integration Bee 2022, regular season problem 10. We have the integral of 4 to the x times 3 to the 2 to the x dx. You know, it's not too unusual to have a number with an exponent like this. That's kind of a standard problem. But then to have this kind of exponent tower is a little unusual. Now, one nice thing, we have 2 to the x here. And then let's notice the similarity that 4 is just 2 squared. So what I want to do to start is I think I'm going to work with this 4 to the x, and we'll write 4 as 2 squared to the x. By exponent properties, I can multiply this in and we could have 2 to the 2x, or I could just reverse them and write this as 2 to the x squared. And that's pretty nice because, like I said, we have this 2x right here. And now that we have this as just 2x squared, I'm going to make a u substitution. I'm just going to call my u equal 2 to the x, noticing, of course, that u squared is going to be this 4x term, or 2x squared, 2x all squared. And before I take my derivative, I'm just going to use this property. If we have a constant value a, we can write this as e to the ln a. So for 2, I can write this as e ln 2. So if I plug this in here and we write our 2 as e ln 2 all to the x, then we could multiply this in and we could have e ln 2x. So then here I'll just take my derivative and we'll have derivative of this is going to be, we'll have e ln 2x, but then with the chain rule, we'll need to bring an ln 2 out front and we'll have our dx. But then I can just solve for my dx value by dividing all this out. So we'll have du over ln 2, but then this e ln 2x, I'm going to write this is just the same thing as u, so I'll write this as a u in the denominator over here. Okay, so now I'll go ahead and make this substitution now that we have everything we need over here. So our 4x again is going to be just u squared, and then we'll have 3, 2x is just going to be u, and then our dx is this thing, du over ln 2 times u. Well, then I can cancel 1u with the 1u here, so we'll just have a u out front here. And then I can take this ln 2 out front of my integral, so we'll just have 1 ln 2 here, and our integral is going to be u 3 to the u du. Then from here, I'm going to use this same trick again on 3. We'll just rewrite 3. I can write 3 to the u. I can write 3 as e ln 3, but this is raised to the u. But then we can multiply that in again. We have e ln 3 to the u. So I'll just rewrite the integral using this value. Then here with just u and our exponential, this is a good place to use integration by parts. I'm going to use the di method, and what I'll do is I'm going to differentiate u because that's going to reduce nicely, and we'll integrate e ln 3u. Differentiating u, we're going to have derivative of u is going to be 1, derivative of 1 is going to be 0, and then here integrating this, we're going to get 1 ln 3 e ln 3u, and then we do it again, we're going to pull another ln 3 out, so we're going to have 1 over ln 3 squared e ln 3u. And now putting together a solution, we need to bring down our 1 ln 2 here. Then our solution is going to be on these diagonals. Now we have this in common, so I'm going to factor this out, and keep in mind this value is actually just 3 to the u. So I'm going to bring 3u to the front of the parentheses. So then for our first term of this diagonal, it's just going to be u over ln 3, and then the next one minus 1 over ln 3 squared. So remembering that u is equal to 2 to the x, so for our 3 to the u, we're going to have 3 2 to the x over ln 2. And here again with our u is going to be 2 to the x over ln 3 minus 1 over ln 3 all squared. Put a plus c on the end, and that's it. We're done. Okay, really like that one, so we'll stop it there. Thanks everyone for watching. Have a great day.